Hello, let's look at a very popular application of maximum and minimum optimization. What's the optimum level of production to maximize profit? What's the optimal level of production to minimize cost? If you're producing a product, what's the optimal dimensions for the container to minimize surface area? Lots of different things that you want to find the maximum value or the minimum value or the best value. So we're going to look at a very basic example in terms of area. This can actually be done with plain old algebra, but it's a good way to show that we can use calculus and derivatives and critical points. So we're going to enclose a region along a wall, and we have 200 feet of fencing, and we want to make the large a region, an area that's the maximum area. Okay, so we've got our 200 feet of fencing. So let's just think about this. The wall is going to be one side of the fence. So I could be kind of silly and make my fenced in area something like this, not drawn to scale. That's always my disclaimer. And make these two sides 99 feet each, which means this side is 2 feet. So interesting configuration. Probably not the best to optimize area, but let's write down, what is the area going to be? Remember, area is length times width, so 2 times 99 is 198 square feet. Okay, so what if we went the other direction? We said, okay, let's make these two parallel sides smaller and this third side a little bit longer. So if I make this side 10 feet and this side 10 feet, then 200 minus 10 minus 10, or 200 minus 20 is 180. So this region here, the area would be 180 times 10, which is 1,800 square feet. We can write it like that. Okay, so we could sit and guess and check and play around all day, but we need a way of getting to that exact value. It may not be a nice number. Okay, so let's think of our situation here. Here's my wall. And I don't know what I'm going to make all three sides, but I'm going to make these two parallel sides are obviously going to be the same length. Okay, so how did we find the length of the third side? We took the total amount of fencing, right? We have 200 feet of fencing, and we subtract off those two sides. So my third side is going to be 200 minus 2x. All right, so I want to calculate come up with a function that will calculate area based on x. And we know area is length times width, so if we think of one of our dimensions, or our width is x, and the other dimension is 200 minus 2x, I now have a function in terms of x that will calculate the area of this region. So if I distribute that x, and I'll put it in descending order, 2x squared, negative 2x squared, plus 200x. Okay, now we've got some restrictions on x because we're talking about a length. So we know x has to be positive, has to be greater than or equal to 0. If x is 0, then what kind of situation do we have? If this is my wall and x is 0, it means I don't have those two sides. So it's basically just like one long piece of fence, which there would be no area. Okay, so what's the maximum that x could be? Well, think about if our fence was the other way. So if we had, here's our wall, and then our fence had no width, so it had no here. So what would make 200 minus 2x equal to 0? So if I take 200 minus 2x set equal to 0, I end up with 2x equals 200 or x equals 100. So if x is 100, then there are only two sides. Okay, so it would be something like this. Okay, so that means x has to be a number between 0 and 100. All right, so we're looking for the maximum area. Okay, so I want the maximum area on the interval 0 to 100. So I'm actually looking for the global maximum on a closed interval, which we've spent time in 4.3 doing. So that requires then that we need the derivative, and then we evaluate the derivative at the critical points and the end points. So the derivative is this thing. Okay, the derivative is, I still can't get away from these smartboard issues. Even at home, they follow me. Sorry. So the derivative is negative 4x. Let's see. Negative 4x plus 200. Set it equal to 0 to find the critical points. And I get x equals 50. Okay, so that's our critical point. So now we have to decide what is going to produce the maximum area. Is it going to occur at the end points, or is it going to occur at the critical point in the interval? I'm sure you can guess already, but we are supposed to check, okay, the end points. What's the area at 0 and what's the area at 100 when x is 0 or 100? Well, if we plug it in back up to here, 0, 0, this is going to be 0. So that's going to be 0 square feet. If I plug in 100, it will evaluate out to be 0 as well. You could do that substitution. Okay, so what if I plug in 50 at the critical point in C? Okay, so I have negative 2 times 50 squared plus 200 times 50 is going to be 5,000 if we do the math. Okay, so what's that tell me then? The maximum, this is the maximum area, occurs at x is 50. So if x is 50 feet, then we get a maximum area of 5,000 square feet. So our picture would look something like this. We would make the dimensions 50 feet on the two sides, which would leave the third side 200 minus 50 times 2, which means 200 minus 100 is 100 feet. And then we can double check if we find area is length times width, we get 5,000 square feet. Okay, now if we look back and think about this, let's go back to our area function. Notice it is quadratic. Every quadratic function either has a max or a min, has a one local max or one local min, which is also the global max or the global min. We know this parabola opens down, so the max occurs at the vertex. Okay, now go back up here. I forgot to mention this, so let's do it real quick. First of all, this is in section 4.3. This one is like number 51 in your homework, and similar to number 38, except in number 38 there's no wall. So you've got 4 sides. So you've got 4 sides to fence. And there you have it, application, optimization.